All right, let's get started. Hi, everyone. I'm Xiaohua from USTC. Because of the time zone differences, I'm recording this video instead of giving it live in order to not cause any lag. So over this part of the lecture, I'll make a short introduction to the GMTSAR software to you guys. So we're going to go over some of the basic designs of GMTSAR and also some of the recent developments of the code. At the very end, I'm going to introduce you guys to some of the newer missions that we are able to support using the GMTSAR software. So GMTSAR is an open source in-SAR processing software. It is able to handle most of the open SAR data. Either you're processing a single pair of interferograms or you are processing a large stack of interferograms using GNU parallel. It also has tools to do simple time series and has a atmospheric correction module inside to do common scene stacking as well. But most importantly for the software, it is completely free and open. That means if you're interested, you can take any piece of the software for whatever purpose to use it by your own. You can either change it or modify or redistribute without any restrictions. It is written in C for most of the processing modules, and we use C shell to connect them together. There will be Python modules in the future. It is already in the master branch. If you are interested, feel free to try some of them. Also, the product of GMT-SAR is fully compatible with the generic mapping tools, which is a pretty famous tool used by a lot of people in the geoscience community in order to produce publication quality figures. And another advantage is that for all the product from GMT-SAR, it should be very easy for you to change it or manipulate it using GMT afterwards. And at the very end, I want you guys to know is that most of the part of the GMT-SAR software is written in a sort of like processing-oriented way that if you are reading just reading through the software, it should be very easy for you to make changes or implement your own stuff. All right, next we're going to go through some of the basic design of GMT-SAR. This is a diagram that sort of shows what we call the processing steps in GMT-SAR. Usually it is divided into 6 processing steps from pre-processing to focusing and alignment of the radar images, and then to back geocoding and interferometry and filtering, phase unwrapping, and geocoding at the very end. The very first step it is called pre-processing. Usually that step takes in data from a variety of space agencies. The main difference between these preprocessors are mainly to deal with the different data formats from all the space agencies. So after this step, the data is generally converted into a generic format for GMT-SAR to read in. That is SLC file, which is the data. Or focus data, or sometimes it's raw if you're using our early SAR data, and LED file, which is the data, orbit file, and also a PRM file, which will be the parameter file. The second step is focusing and alignment. So focusing is the part that converts the raw data into a single log complex, that is a SLC file. And alignment is a step that sort of co-registers radar images to the same reference frame. And after that step, you can consider the measurement is in the same reference frame as what we call the master image. And the third step is called back geocoding. This normally involves projecting topographic information from geo coordinates or long lat elevation to radar coordinates, which is range azimuth and elevation. So by doing that, you are able to compute what we call a very large lookup table that is used later on, either for correcting topographic phase or doing actual geocoding. The fourth step is doing interferometry because the first three steps basically ensures that you have the tools to do interferometry. And during the fourth step, you are actually doing that. And after doing interferometry, you get an interferogram, and then you can filter the interferogram either with just Gaussian filtering or maybe use Goldstone filter, which is spectral filter. And after that, you should be able to perform what we call phase unwrapping. And this step we use is external software from like Stanford. This is called Snafu. We use that to do phase unwrapping. And then at the very last step is using the information that we get from the third step to do actual geocoding. We listed some of the modules here, which sort of shows you like what program is called during each of these steps. But generally speaking, the first 3 or 4 steps usually uses most of the core modules that we developed for the GMTSAR software. And then the later 3 or 4 steps mainly uses GMT to do the post-processing. And most of them are associated with geocoding or plotting or masking and figuring out coastlines, et cetera, et cetera. And for most of the shell scripting part, we are trying to replace them with sort of the newer generation Python code. And other than these 6 steps, there are also other some more stuff that I want to introduce to you guys, like other modules. Like other than processing the data, you can also use them to, for example, correct the data, such as making tide correction. Or if you want to create a multi-aperture interferogram, you have the capability of doing that with MAI processing as well. Also, we are able to do ionosphere correction by using the split spectrum code we implemented, I think, a few years ago. And also, you are able to split aperture. This is part that's sort of implemented to do MAI processing. Other than that, we also have time series tools so that you can connect all the measurements from the interferograms to build a long time series. We also have data manipulation tools so that once you download a large stack of Sentinel-1, for example, TOPS data, you can reorganize them and define your own frames. Or if you feel that your area is only just a small piece of a larger interferogram, you can cut the data and only process that small piece. So other than all these scripts, there are also what we call the top-level scripts. For example, P2P processing. This is used for processing a pair of interferograms. And we also have scripts to process a large stack of interferogram, which is called batch processing. But internally, it is calling just this P2P processing multiple times, just calling it again and again to deal with a large stack of data. It is similar case for this P2P S1 TOPS frame. This is used to deal with the multi-subswath kind of scenario. It's the same scenario for ALOS2 as ScanSAR data as well. When you have like multiple subswaths, you can use these scripts. And also, there are some prior scripts that is written to deal with TOPS data, such as pre-proc batch TOPS, etc. Here are some recent developments. I'm not gonna go through all the details, but the most important thing is that I want you guys to know that we are actively developing the software, so don't hesitate to make a feature request or tell us that what is needed for you. There's an example from last year that someone asked us a question saying that, do we have a parallel processing script for Sentinel-1 TOPS at the correlation step? My answer from last year is that no, we don't have that yet because it's easy to do and you should be able to write it very in a very simple way using GNU Parallel. But this year we already put that into the distribution. So if you feel that is really needed and you don't know how to write it up, don't like hesitate to bug us. That's sort of our job. Here are some examples for doing ionosphere correction. You can download them from GMTSAR website with download examples. They are available for ALOS-1, ALOS-2, and also Sentinel-1. I think it's doable for other satellites as well, but the filtering step might take a while to run. This is sort of a summary of some of the traffic data on GitHub. We started collecting them in 2022, I think. But just during the last year, we have about 140 issues opened. They are pretty much addressed up to date, but you see a lot of them are still open because we leave them open for about 6 months. And during the past year, averagely speaking, there are about 415 what we call unique clones every 2 weeks. So that corresponds to about like over 10,000 per year ish. And this is sort of a plot for the past and ongoing or maybe future SAR missions. either starting from ERS. I mean, you also have CSAT here. We have ERS, ERS2, and NVSAT. You can recognize some of the names. For all these that are marked with red stars, we do support them currently at the in the GMTSAR software. And the orange ones are currently being developed. I mean, the code are already in the master distribution, but since we have very limited experience with the data, they may get changed again in the short future. And they also have these yellow stars, I call them, that will be supported. We do have a preprocessor already for NISAR simulated data, which is simulated with Sentinel-1 data, but since we don't have any real NISAR data yet, it is marked as yellow. Also we will support ROSEL. Most of the open SAR data will support them. I'm gonna end this session with a plot here. This is a diagram that shows a number of acquisitions over a specific area on Earth that you can get relative with time. I mean, you have a lot of like free data, either it's from ERS, NVSAT, ALOS, or Sentinel, or NISAR. This is a time when my PhD advisor, David, started working with INSAR. That is when I started working with INSAR. I think both NVSAT and ALOS1 just dead. So I don't have any new data to work with until 2015. This is when you are starting to work with INSAR data. This is sort of at the historic high. And this is only counting acquisition numbers. It hasn't accounted for the change of data quality yet. If you think about the quality change of the INSAR data, this diagram might be more dramatic. So it's probably the best time for you guys to work with INSAR data. And I'll stop here and leave some time for questions.